Okay, chemistry, we're on to the next lesson in the acid-bases unit, and now this deals with an experimental technique known as titration, which is used to analyze acids and bases and how they react with each other. So what is titration? Titration is the addition of a base of known concentration into an acid of unknown concentration in order to determine the concentration of the acid. So over there you see a titration setup. So the process can also be performed with an acid and base reversed. So it could be that the base is unknown and the acid is known. But we will use a known base and an unknown acid in our example. So the known base is called the titrant. And that's in a piece of glassware called a burette. It's a long, narrow piece of glassware. It has a little knob at the end. They call it a stopcock, and you can open and close it to let the titrant drip down into the flask that you see below. The unknown acid is called the titrand or analyte. I like to use analyte because titrand and titrant sound too much alike. So the titrant is what's up in the burette that gets dripped down into the analyte. The analyte is what is of unknown concentration. You know the volume of it. You can see how much you have in the flask. You can measure the volume, but you don't know what the concentration is. Because remember, the acids are always in an aqueous solution, in a water solution. The usual procedure is to drip the titrant into the analyte using a long glass tube called a burette with the valve called a stopcock to control the flow. Okay, so we're going to put a table together. And what we're going to do is we're going to take two very common strong acids, sodium hydroxide and hydrochloric acid. So the first example we will see is the titration of a known strong acid, hydrochloric acid, with a known strong base, sodium hydroxide, so that we can see how they react with each other. After the Na, the sodium, and the Cl, the chloride, dissociate, we can observe the reaction of the H+, the hydronium ions, and the hydroxide ions. That's really what we're interested in. The chloride and the sodium just become spectator ions. So we're going to do a first titration. Now up above, in the column on the left, we have hydrochloric acid, and in the column on the right, we're going to add that to sodium hydroxide. Okay, so what we're going to actually be dripping is the sodium hydroxide into the hydrochloric acid. Now, first of all, as I said, the chloride and sodium ions they're going to dissociate because solubility rules tell you that they will dissociate in this situation. So you end up with Na plus and Cl minus, and they break away, but they simply become spectators. So we're going to put them off to the side. We're not interested in the sodium and the chloride. We're interested in the H plus, the hydronium ion, and the OH minus, the hydroxide ion. So that's what we're going to put down in the first row there. H plus for hydronium, that's the acid, and OH minus for the base. And when you put those two together, you get water. So when those two react with each other, we're going to get some amount of additional water. Now keep in mind these solutions are all water-based. They're all aqueous. So when we talk about water, we're talking about additional water that we get out of this chemical reaction. So initially that's going to be 0 in every case. So we're going to go ahead and do a first titration, which really isn't much of a titration. We're going to start with 1 mole of the HCl, which means since it's a strong acid and totally dissociates, it's going to give us 1 mole of hydronium ions. And we're going to start with no hydroxide, no sodium hydroxide, and therefore no hydroxide. So we haven't dripped anything from the sodium hydroxide is up in the burette. That's what's going to get dripped down, and we haven't dripped any of it down yet. So that's 0 OH minus. And we're going to start off always, each of these titrations is going to be separate. So we're going to always start off with no water, meaning no additional water. So at the end of this, you're still going to have your 1 mole of hydronium ions, H+. You still have 0 moles. You haven't done anything yet. And that means you're going to produce no moles of additional water from the reaction of the hydronium and hydroxide ions. So the pH there We're going to come over and calculate it from the hydronium ion concentration. The pH is the negative log of the hydronium ion concentration, 1.0. You know this formula, and that gives you 0, so your pH is 0. So we're going to come over here and we're going to graph this, and we're going to see what is called a titration curve, and the shape, it has a characteristic shape that you're going to see here as we do this. So we started off with 0 moles of OH minus, so we're going to put the dot as close to 0, 0 as we can. So the final state, there was no change. There's 1 mole of, it's 1 molar, but really 1 mole of HCl, and that gives you a pH of 0. If we assume that we're in 1 liter of solution, then 1 mole and 1 molar are the same. Alright, now we're going to do a second titration. This is totally independent of the first one. So we're going to start off again with H plus and OH minus. Again, we're not interested in the Na or the Cl. So we're going to start off with 1 mole of hydronium, and now we're going to add 0.5 moles, half a mole of hydroxide. And again, we start off with no moles of water that's been added to the solution to the solutions. So now what happens is 0.5 moles of OH minus reacts with 0.5 moles of hydronium H plus. In other words, it's 1 molecule for 1 molecule, or 1 ion for 1 ion of each. So you can only react as much as the amount that's the least. So in this case, it's the hydroxide is 0.5 moles. So it's going to react with 0.5 moles of the H plus. And when it does that, that means 0.5 moles of the H plus has not been reacted with the OH minus. So that's what you have on that final line. That's what you have left over. Now, on the hydroxide, you've used it all up, 0.5 moles reacting with 0.5 moles of H plus. Now, when that happens, 0.5 moles of OH and 0.5 moles of H plus, you're going to get 0.5 moles of water. So that's what you see. That's additional water that's been added because of that chemical reaction. So that's what you see on the final line of H2O. So stop for a minute and kind of piece out these numbers. Be sure that you understand what they're saying. You have in both cases, in all cases, in fact, in this example, 1 mole of hydronium, H plus. Now you're going to add half a mole of OH. So half a mole of OH will react with half a mole of hydronium, H plus, to produce half a mole of water. But that still leaves you with half a mole of H plus that wasn't reacted. So that's what you see down there under H plus on the final line, is the half mole that was not reacted. So we can now use that. That's what's still in the solution. We can use that to calculate the pH. So we're going to take that number, and the pH is the negative log of that 0.5 that's still in solution as H plus or H3O plus, and that gives you a pH of 0.3. So let's go and graph that, and we're going to put that right there. So the final H plus concentration is now 0.5 mole, half of its value in titration 1. However, even though it's only half the value it was in the first titration, the pH has risen only slightly. It's gone from 0 up to 0.3. So you see the line down at the bottom there is still fairly flat. Now we're going to do a third titration. We're going to start off again, as always, with 1 mole of hydronium. Now we're going to add almost as many moles of hydroxide, OH minus, 0.9. So we still have more hydronium, H plus, than OH minus, but it's getting very close here. So again, we're starting off with no excess water that's been reacted. So now if you react 0.9 moles of OH minus with 0.9 moles of H plus, that's going to leave you with 0.1 moles of H plus that did not get reacted. Almost all of it did, but not quite. We've used up all the OH minus again. In all 3 of the cases above we did. And so now that's going to give us 0.9 moles of OH, reacts with 0.9 moles of hydronium H plus to give you 0.9 moles of excess water, additional water that was added to the solution. So now we can compute the pH using the 0.1 moles of hydronium. We bring it over here and we get negative log of 0.1, which is 1. So now we're going to go and plot that, and it goes right there. So the final H plus concentration is now 0.1 moles or molar. That's only 1/10 the value of titration 1. However, the pH has only risen a little bit more. It's gone from 0 in the first titration only up to 1. I mean, that's on a scale of 14. So it hasn't gone up very much. So even though you're adding almost as many moles of hydroxide as you have moles of hydronium, as long as there's more hydronium, the solution is going to be large. It's going to be very strongly an acidic solution. 1 on the pH scale is a strong acid. Now we're going to do a fourth titration. So there's the 1 mole that we always start with for hydronium. And now we're going to titrate in the same amount of hydroxide, 1 mole to 1 mole. We start off again with no excess water. So now what happens is we end up with no moles of H plus because it's been totally reacted with the OH minus. That means we also have no moles after the reaction of OH minus. And when you've reacted the 1 mole of hydronium and the 1 mole of hydroxide, that's H plus OH minus, you get 1 mole of water, H2O. Now there's no way to calculate the pH here because you have no hydronium, no H plus anymore. But what we know about water is when there is no acid and no base in it, just pure water, that it has a pH of 7. So we'll come over here and we're going to put that in. So it's the negative log of 10 to the minus 7th is 7. And that's the pH of pure water. So we're going to go over and so now we're going to plot that point. And you can see how much it's jumped up. We had only a small amount of strong acid in the last titration, only 0.1, and yet it held the pH down at 1. Now that we're neutral, no longer have any acid or base, then the pH jumps suddenly all the way up to 7. Here the concentration of hydroxide exactly equals the concentration of H plus hydronium. Both are 1 mole. This is called the equivalence point. This means that only H3O plus concentration is 10 to the minus 7th, which is the autoionization of water. And so we're going to put that into our pH calculation to get a pH of 7. Now titration number 5. We start with no excess water again, and we're going to still have 1 mole of hydronium. And now we're going to put in more hydroxide. 1.1 moles. So for the first time, there's more OH minus than H plus. We're going to start off with no excess water again. So that means all of the H plus is going to be reacted. So we're going to end up with none of that. The hydroxide, OH minus, 1 mole of it is going to react with the 1 mole of H plus, but that's still going to leave us with 0.1 moles of hydroxide, OH minus. And when you reacted the 1 mole of hydronium H plus and the 1 mole of hydroxide OH minus, you've got 1 mole of excess water. And that will be the case all the way down for the rest of the titration. So that's excess water doesn't contribute to the pH. So now we need to contribute our pH. But how do we do that? We don't have any more hydronium H plus, that's 0. But what we have is hydroxide OH minus, that's 0.1 mole. And we can calculate the pOH, and then remember the formula that pH plus pOH equals 14. So we're going to come over here and use that formula, and there it is. So the pOH is negative log of 0.1. That's the hydroxide concentration. If we subtract that from 14, we get 13. And that's the pH. So we have to kind of go a roundabout way to get the pH in this case. So now we're going to go and plot that. And look how much it's jumped up. So going from 0.9 OH to 1.1 OH, not a very big increase in concentration. You've jumped all the way from 1, that's the third dot from the left, all the way up to 13, that's the top dot there. So now there's more than enough OH minus to neutralize the H plus and still have some NaOH left over, really OH left over. This means that the solution will be basic. Since we don't have any H3O plus to calculate pH, we calculate the pOH. and subtract that number from 14 to obtain the pH. So 14 minus the negative log of 0.1, negative log of 0.1 equals 1. So 14 minus 1 equals 13. Now titration number 6. Again, we're starting as all of them with 1 mole of H+. Now we're going to go all the way up to 1.5 moles of OH minus. And as usual, we're starting with no moles of excess water. So now we've used up all of the H+ again. There was more than enough OH minus to react with all the hydronium H+, so all the H+ has been used up. Now what we needed to react with the H+ was 1 mole of OH minus. So that reacted, and that still left you with 0.5 moles of OH minus left over. So the 1 mole of H+ and the 1 mole of OH minus that reacted produced 1 mole of excess water. Again, the excess water does not do anything to contribute to the pH, doesn't change the pH. So now we're going to calculate the pH the same way we did before. We're going to calculate first the pOH and subtract it from 14. 14 minus that pOH is going to equal 13.7. So now we go over to our chart and we're going to plot that. There's 13.7 at 1.5 moles of OH minus. So as we continue to add OH minus, here we neutralize all of the H+ and have 0.5 molar of OH minus remaining in the solution. So there it is. There's the pOH is negative log of 0.5. So 14 minus that number is going to give you 13.7. Finally, we'll do one more titration. Okay, so now we have, again, starting with 1 mole of H+. Now we're going to put in fully 2 moles of OH minus. And we start with 0 moles of water initially, excess water. So now there was more than enough OH minus to react with all of the H+, so we now have no more H+. Now if 1 mole of OH minus reacted with the 1 mole of H+, that still leaves you with 1 mole of OH minus in the solution. And the 1 mole of OH minus and 1 mole of H+ produced 1 mole of excess water. So now we're going to go ahead and use the concentration of OH minus to calculate the pOH over here. And you subtract that from 14 to get the pH. So the negative log of 1 is just 0. So 14 minus 0 is 14, so that's the new pH. And we're going to plot that. Finally, we have added 2.0 molar of OH minus. This means we have neutralized the 1 molar of H+ and have 1 mole of OH minus remaining in solution. This results in a pH of 14, and there's the calculation. Now let's go over some terminology that's used. This is a classic shape of a titration curve, and you saw how it was developed. So this shape is called a titration curve. The point where the amount of strong base and strong acid are equal is called the equivalence point. The OH minus and H+ ions are equal and neutralized to water molecules. The area before the equivalence point, remember we started at the bottom, worked our way up to the top, that's called the pre-equivalence point, where H+ ions make the solution acidic. You always had, in those first 3 titrations, you had more H+ than OH minus. Up above the equivalence point, the area after the equivalence point is called the post-equivalence point, where OH minus makes the solution basic. This is the characteristic S-curve of a titration of a base into an acid. We started with 1 mole strong acid and slowly titrated from 0 to 2 moles of strong base. As almost half of the strong base is titrated from 0 to 0.9, the pH changes very little in that lower region down there. In the short space from the small amount of excess H+, that was 0.1, to the small amount of excess OH minus, that was 0.1 of OH minus, the pH jumps from 1 all the way up to 13. So it does that very quickly as the solution changes from being slightly acidic to slightly basic. Finally, in the base range from 1.1 moles up to 2.0 moles of OH minus, the pH gradually increases from 13 to 14. This titration curve represents an acid being added to a basic solution drop by drop. The solution begins as a base and passes through the equivalence point and down into the acid range as more acid is added. There's the equivalence point where the pH is 7, and then down below the post-equivalence region. Alright, and that takes care of our lesson on the titration of a strong acid and a strong base. In the next lesson, we'll see what happens when we have either a weak base or acid.